Dear ladies and gentlemen, it's quite nice to have the opportunity to introduce our membrane-based technology for gas drying. At the beginning, I will speak about natural gas drying. This will be potentially disappointing for some one of you, but at the end, I will switch also to hydrogen. Well, for sure you know natural gas is an environmental friendly energy source because of the high amount of hydrogen in the methane molecule. If you burn natural gas, you are saving 50% of CO2 emission in comparison to carbon combustion and 30% in comparison to oil combustion. And because of this, the infrastructure for natural gas in Germany is growing continuously and also in Europe. And we have a complicated pipe system and we have underground storage systems. In the moment, there are approximately 50 underground storage systems in Germany, and there are more than 20 billion cubic meters natural gas in. This is the amount that is equal to the consumption of 3 months in Germany in wintertime. It's a huge amount. However, if you store the natural gas in such caverns, the gas is get moistured. And therefore you have to dry the natural gas if you take it off from the underground storage system to prevent condensation of water in the pipes, to prevent methane hydrate creation, what blocks valves, etc. So every gas have to be dried if it's coming out of the underground system. Of course, there's an existing technology what is used everywhere in the world, and this technology bases on the using of this liquid triethylene glycol, TEG, what is a quite hydrophilic liquid, and this liquid is streaming in a counterflow against the wet natural gas. The gas is giving over its water to the TEG, then you have the dry natural gas, and then of course you have the wet glycol. And now you have to dry the glycol, and because it's very hydrophilic, the temperature for drying is quite high when you're using distillation, around 200 degrees C. And of course this high temperature consumes a lot of energy, but this is not the biggest disadvantage. A higher disadvantage is that the glycol starts to crack a little bit. And this reduces the lifetime of the glycol, and it creates also crack gases, and these crack gases finally have to burn, of course, by consumption of methane, and so you have a remarkable CO2 emission. And besides this, the natural gas production from such an underground system is not continuously. If you have a very mild winter time, then it's not working. But to be able to start this drying system immediately, the system always have to kept on high temperature, independent if the natural gas is produced or not. And this high temperature of 180 degrees C in the standby mode also consumes a lot of energy. Well, and because of this, we decided to substitute this distillation process by a membrane process. And the first advantage, of course, is you can run the system now at a much lower temperature of 120 degrees C. And because of this, you have a lower energy consumption, you have no glycol cracking, longer lifetime of the glycol, and you have no burning of the crack gases, what is of very big advantage, no CO2 emission. And of course, you can easily switch off the filter plant because you can very short time switch on again, and therefore you have no energy consumption in a standby mode. Well, the task of our institute was now to find a membrane what is able to separate the water from the TEG. And what we found had been a zeolite. May you know, zeolites are aluminosilicates crystals with defined pores inside, and in this case we choose a zeolite A, with a pore size that water can go in, but the TEG molecule cannot go in. And if you prepare these zeolites as a homogeneous layer, then theoretically it would be possible to separate continuously water from the TEG by a filtering process. And this is what we have done in the institute. We developed a technology to prepare the zeolites as a very thin intergrown layer on top of a porous ceramic substrate. You can see here some single crystals, but this is the intergrown membrane layer. And this nanoporous alpha alumina substrates is shaped in this geometry. These are 4 channel tubes of 1.2 meter length, and this membrane layer is inside of these channels as a very thin layer. And then practically it is used like this. This is a crack through the membrane. Here this is the substrate, this shall be the membrane layer. And then the red TEG is flowing into the tubes, and because of vacuum, only the water is going through the thin zeolite membrane layer, through this layer, coming out here at this side of the tube. And at the end of the tube, or arrangement of several tubes, you have the dry TEG. Well, our project partner, DBI GOT in Leipzig, tested the membranes in their labs, and they also made a process development in the labs. And what they found out, the TEG can really be dried by the membranes down to 0.5 weight% of water, and they also tested long-term stability over several months and found no changing of the stability. And basing on these results, then they engineered a first pilot plant, and in the time between 2015 and 2017, this pilot plant was installed in an underground storage system in Stassfurt, what is not far away from here. This underground storage system is owned by Energy. Well, and this is a view onto the whole plant, what is directly connected to a classical drying unit. Here we have the gas pipes feeding the plant with the wet gas. Then there's a very small TEG adsorber where the water from the natural gas is given over to the TEG, and then the red TEG is dried by the membrane unit, and then there are also some other containers for with tanks, with pumps, and of course with the control unit. This is the whole equipment. And now let's have a look into the container with the membranes. Here inside, this is a membrane plant. There are 3 parallel lines. In each lines we have 3 modules with 1.2 meters long tubes, and in each module we have several of these tubes. We are looking into these 4 channel tubes now, and the TEG, the wet TEG, is flowing into the tubes in this direction. What means here in this direction, and here on the outside we have the vacuum, and over this way the water will be collected. Quite simple technology. 225 zeolite A tubes are installed in the plant, what are around 20 square meters membrane area. Well, this plant is running parallel to a classical drying plant, including all switch on, switch off times. What we found out, we could always dry the TEG below 0.5 weight% of water, and the 20 square meters of membrane area are able to treat 10,000 cubic meters natural gas per hour. Well, over the last 2 years we collected a lot of results. I show you at first only the results from the last period, the Richter 17-18. In this time, the filter plant dried 8 million cubic meters natural gas. We separated 4 tons of water from the natural gas. And this is the most interesting result. We found that in comparison to the classical technologies, the OPEX are reduced by 30%. And this is really surprising because this filter plant is not optimized up to now. And by the way, we also saved 9.2 tons of CO2. Well, how is it's going on? Of course, we're optimizing the process. We are advertising the process, what I'm doing here in this moment. We hope to be able to move the existing plant to another facility, and with 2020 we start to scale up to a large plant what is able to treat 200,000 cubic meters natural gas and per hour, and then later on we hope to be able to install up to 50 units all over Europe. However, we are not only fixed on the underground storage systems, it is also interesting to go to the gas exploitation, then, because also if you exploit the gas is wet and have to be dried. And an also interesting topic is the drying of biogas. If everything works fine, then theoretically, with such a big plant, we would reduce the CO2 emission by 500 tons a year, and with 50 of these plants by 25,000 tons a year. Well, however, I promised also finally to speak about hydrogen, and of course, why only dry the TEG? Why only indirectly drying the gas? Why don't drying the gases directly? And to testing this, we do have a test equipment in our labs, but it's only lab scale, I have to underline. And there we can mix different gases, hydrogen, CO2 or methane, with a certain amount of water. In this example it's 50-50, but we can mix in every combination. We can go pressures in between also up to 15 bars and up to 300 degrees C. And what we find out, for instance with the zeolite A membrane, but also with other ones, is really possible to separate the water from the gas stream up to 100%. It means all the water what we are feeding there is going in this direction, and here we have really the dry gas. It's of course depending on the conditions, on pressure and temperature, but it's possible also to dry directly these gases. And for what purpose you can use it? Of course, you can direct natural gas drying or other gases dry. And most impressive or most interesting for us in the moment is the shifting of equilibrium in chemical reactions to remove the water from a reaction what is producing water as a byproduct. Okay, with this I come to the end. I try to show you that the drying of natural gases with zeolite membranes is of course innovative, that's quite clear. It's economic, it's also environmental friendly, and we are investigating the direct gas drying, and there we are searching for partners for doing this. Please speak with us, talk about a potential application, visit the running pilot plant also together with us in Stassfurt. These are my contact data. It's allowed to take a photograph of this transparency. Yeah, thank you for your attention.
Thank you very much, Dr. Hannes Richter. Are there any questions from the audience? So many people taking notes and pictures. No questions? Okay, then let me have the first one. You talked about the OPEX, minus 30%. What about the CAPEX?
Yes, the CAPEX is in the same range than for the classical technology. We are only slightly above this because the membranes are quite expensive in the moment, but we have a strategy to change the membranes. I showed you the 4-channel geometry, and what we are doing in the moment, we are going to a 7-channel geometry, what increases the membrane area per element, and then it's becoming remarkably cheaper, and then we should be in the range, exactly in the range of the classical technology. Yep.
Thank you very much. Are there any further questions now? Okay. If not, as invited by Dr. Hannes Richter, please go to the booth, discuss the topic any further on booth E45 in this direction.
Yep.
Thank you again.
Yep, thank you.